Welcome to all you grade 10 mindsetters. It is a Tuesday. That means we're doing physical sciences. I am Luni, and joining me in studio today is Tracy. Tracy, how are you doing?
Fine, and you?
I'm good, thank you.
It's nice to meet you.
I know, hey? Thanks
Yeah.
for having me on a Tuesday,
it's okay.
finally.
Anytime.
So what are we doing on today's show?
Well, today we're going to do circuits. We started that a little bit last week, a little bit of introduction. So today we're going to do resistance, we're going to do Ohm's law, and we're going to do a couple of calculations. We're going to really cool, fun simulation to play with. So I think it's going to be a good one.
Mindsetters, you heard it. Electric circuits. Science, guys. It's all that stuff. I did it at school, but then it wasn't my favorite subject. But anyway, guys, to keep in touch with us on Facebook, make sure you go onto facebook.com/LearnExtra. Our handle on Twitter is @LearnExtra to download all your show notes, the videos, the schedules, past exam papers to get you prepared for the coming exams. You can go to learnextra.co.za/live. Guys, we also have Career and Daba coming up. It's from the 20th to the 22nd of June. So make sure you go register yourself. It's for free, and Mindset will be there. You can meet me and all the other presenters. You can go into careerandaba.co.za. So all that said, I think, Tracy, we can start the lesson.
Thank you, Looney. Okay. Well, guys, we're going to go straight into it. Like I said, it's the second part of electric circuits. Last week we spoke about potential difference. We spoke about current. And now we need to talk about a thing called resistance. But before we get there, let's just talk about what we are going to do today. We are going to discuss resistance in an electric circuit, what it is, all of that sort of stuff. We're then going to look at resistors in series and in parallel, because that's really important how they're connected. We're then going to define and discuss Ohm's law, very, very important law, and we're going to do a couple of calculations using Ohm's law, okay? So we're still keeping it fairly simple. Next week, so make sure you don't go anywhere, next week we're going to do the more complicated circuits with circuit diagrams and that sort of thing, okay? But first of all, let's just talk about the whole concept of resistance. Now, we know that in an electric circuit, we put metal conductors in because they conduct electricity really well. Now, what is actually happening is the electrons are moving from one part to the other, but how is that possible? If we look at the metallic bond inside a metal, remember that inside this bond, we're going to have our positive cause, this part here, okay, and I don't think you can actually see that. Let me do it in another color, say, put it in white. So we have our positive cores, which are stationary, okay, to a certain extent. So they are the nucleus with the inner electrons of each of the metals. And then around them, we have our delocalized electrons. Remember, those are the electrons that would sit in the valence shell of a metal. Those delocalized electrons can be given, when given enough energy, will move through the conductor. So they're able to flow. They can move from one side to another as long as we've given them energy. Okay? How well or how badly they move depends on resistance. It depends on the structure of the metal inside. Now, remember, last week we defined electric current as the flow of charge, which can be either negative or positive, but specifically in a conductor, it's the flow of electrons. So with electricity, we are concerned with the flow of electrons because it's the valence electrons that move from one side to another. A good conductor, which is what we want in circuits most of the time, has very little resistance. It allows current to flow really easily. However, we get bad conductors. Bad conductors are actually good. That sounds a little bit of a contradiction, but they are. Because we can make use of the fact that they're bad conductors because they offer resistance, and we can make use of that in our circuits to perform different functions. So in a traditional light bulb, for example, we use the fact that tungsten, the filament, gets very, very hot because it has a very high resistance. But it gets so hot it burns white. It has that white, bright light that we can use. That's a good thing, okay? Now, wrong way. Let's go forward, shall we? Because we've done that. Now, what is a resistor? Well, first of all, we're going to define a resistor. It is a component in a circuit which does exactly what its name says. It resists the flow of charge. It makes it difficult for the electrons to move through it. It is generally a bad conductor. It should be a bad conductor, but it's still going to be metallic, okay? So we're not going to go and put in an insulator. So please understand the difference. I'm not going to put plastic into a circuit because it's a bad conductor, because it doesn't conduct at all, and in fact will just melt and burn, and it's just silly. So when we talk about resistors, they're still going to be metallic, okay, or semiconductors, so metalloids, but they still going to be able to conduct a little bit. They're just not very good at it. So they're not as good as, for example, copper. Copper is a great conductor, so it's not good for a resistor. It's said to have a resistance, and its symbol is R. So whenever we put resistance or a resistor into a circuit, or we put it into an equation, we use R, okay? Now, what happens with the resistor? Well, electrical energy is converted into other types through the resistor. So, and most of the time it's heat, but we can get light, maybe we get sound, maybe we get kinetic energy, all sorts of things can happen here, okay? And resistors can be connected in series or parallel. Now I want to show you a quick simulation. Remember, we use FET all the time. I absolutely love that website, phet.colorado. It is absolutely amazing. Get so much really cool stuff in there. Now, what I've got over here is a simulation where it's a simulation, okay? So it's exaggerated, but we can deal with it. We have a battery in the middle, and over here, the little, I'll stand this side because there's actually more of the stuff on that side. We have an ammeter which is connected to a windmill. Basically what's happening is when I play this, I just want you to see, don't worry about everything else that's happening. The windmill turns because it's like water falling on it, okay? And what we're going to do is I'm going to just make the resistance a little bit more. So I'm increasing the resistance to make the voltage a little bit less. Let's make it 2 or thereabouts. So I've changed the resistance, I've changed the voltage, and I want you to see something. First of all, on the hot-cold meter, if you watched, it actually is got cold. I'll speak English for you too. The current is quite low, but this also has a fairly low resistance, which is fine. But if you watch carefully, as the little blue electrons are going through, you can see, and they're a browny grey color, inside my resistor, which is the big box, okay? Let me just, so the resistor, so now we've got a shot of it, is this part here. Okay, that's what when I'm talking about the resistor, it's over there. Now, just now, what I've written will disappear, so just watch carefully. The electrons are my little blue things that are going around, and these funny grey circly things that are bouncing up and down, those are the cores. So that's referring to the inside, the metal cores that don't move, they can't go anywhere, they can't move backwards and forwards, okay? And over here, let me just take that away, this fan, if you want to call it that, that's really just measuring the current so we can get a current over here. I'm not overly concerned about the current and that sort of thing right now. What I want you to see is that as I increase the resistance, so what I'm going to do is I'm going to increase the resistance inside my resistor. So I'm going to increase the number of little cores there are, and I want you to see what happens. I'm going to keep the voltage the same, so let's get rid of that. Okay, and I'm going to increase my resistance. Look how much slower, it becomes so much harder for the electrons to move through. That it still stays fairly cold, okay, but in order for the electrons to get through this resistor, I need to increase the voltage. So I need to give them more energy. And then what happens is as they move through, the resistor gets hot. They're showing this by making it change color, all right, and it's getting hot because the electrons have lots of energy, and as they're moving through, they bump into the cores, they bump into the other electrons in the resistor, and they transfer their kinetic energy to the resistor. Doesn't necessarily result in kinetic energy from the resistor, so we're not going to see the resistor bounce up and down, but the energy that's there can be used. Okay, so that makes it a bit easier for us. Now, when we look at resistors, so we're going to go back here, all right, and we look at, well, you know what, resistors can be connected in a couple of ways. And we've got to think carefully about what a resistor does. A resistor makes it difficult for current to move through it. So in terms of an analogy, you can almost think of a resistor as like an obstacle course. So the more obstacles we put in its way, the harder it is for the electrons to move, okay? So if we connect resistors in series, as this diagram shows, nice and simple. Now remember, we would have connected to the whole circuit, it's just part of it. 1 resistor, 2 resistors, 3 resistors, and we're going to use my favorite thing on the board. I absolutely love these things. Let's use the stars. The stars represent the current, okay? So the current comes along, goes through, gets its first obstacle, second obstacle, third obstacle, and you know what? Lots of resistance. All the current has to go through each of the resistors, and it's just hard work. So what we're doing, when we add resistors into a circuit in series, we are increasing the total resistance of the circuit. We're making it more difficult, which in turn means that the total current gets smaller because it's hard work, okay, for the electrons to get through the circuit. When we look at the voltage, we spoke about this a little bit, I think, last time. The voltage splits between them. Remember, voltage is potential difference. So what we're looking at when I look at the voltage there is the voltage is measuring how much energy the electrons lose every time they go through a resistor. If these 3 resistors are the same, so they all say 10 ohms, then all electrons lose the same amount of energy every time, and each voltmeter will read the same, except the total, okay, which now has a star on it, because the total will measure all 3 of those added together, because it measures how much energy did they have when they started, how much energy did they have when they finished, okay, and tells you the difference. Whereas V1, V2, V3 just measures how much energy did they lose at each obstacle, okay? So what we have here is the equation then. Oh, and that was my mistake. That should be a 3. Sorry. Oops. Oh, that looks terrible. Over here, this should be R3. Sorry, guys. When we add resistors in series, the total is simply all of them added together. Grade 10s, when it comes to the way you write these down, these little subscripts, and by subscripts I mean these things, the I total, the R1, all of those sort of things, that's like naming the resistor, okay? So that's not just saying, so for example, with Looney and I'm a girl, and if you just called me girl, it could get a little frustrated, okay, because we're both girls. So if you just said girl, we wouldn't know who you were talking about, okay? But if you call Looney, then we know we're talking about Looney. She's a girl whose name is Looney, and I'm a girl whose name is Tracy. It makes life easier. So yes, we know we're dealing with resistors, but you need to name them. So there's little subscripts of the names. It makes life a lot easier, okay? So, next one. We can also connect our resistors in parallel. Now, this connection is very important, because what happens here is our electrons come along, and they get to a point where they go, oh, wait, now we have a choice. Wonderful, 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 okay? It's like if you only had one corridor at school to go from between all your classrooms, man, you guys would never get anywhere. And I know I struggle with my learners because, you know, it's nice to be late and stuff, and we fight with them all the time, but, you know, you're teenagers. But there's lots of corridors, so they don't really have an excuse. There's plenty of paths to take. So what happens here is my current actually will split up. So some of it will go over there, and some of it, let's use the flowers, will go over there, and some of it, let's use that one. Oh, I love these pens. I want some of these. We'll go over there, and then they all join up together, and off they go, okay? But the point is the current splits, plenty of paths. The more paths we have, the more choice, the less resistance, okay? So this is like saying, well, as long as the total number of kids get through all 3 of these obstacles, we don't really care how many go through this one, or the R2, or the R3. And let's be honest, electrons are like teenagers, what I say all the time, they're lazy. Well, actually, mostly like humans. We all like to do nothing if we can have it. Or actually, we just like to go the path of least resistance. So what would happen if, say, R1 is my smallest resistance, the most of the current will go through there, because it's easy, okay? It's like having the choice between running on the road or running through mud. If I have to run, I'm going to run on the road, because it's easier than running on mud or on grass, okay? Least resistance. That also changes the way we calculate resistors in parallel, okay? In that resistors in parallel are calculated with a very different equation. We can't just add them together. We've got to do an inverse, and I am going to show you a problem with this, because it's very important that you see it. 1 over R total, 1 over 1 plus 1 over R2 plus 1 over R3. The maths here is so important, grade 10s, okay? Now, quickly before we go to a break, resistance is measured in ohms. It's named after a man called George Simon Ohm. I'll tell you a little bit about him just now. And its symbol is R, okay? Nice and simple. Ohms is an omega sign. It's a little like a Mexican hat, okay? And I think, Looney, we can take a little break, and then when we get back, I'm going to do a quick calculation with resistance. I think it's important, and then we're going to do Ohm's law.
All right.
Yeah.
Mindset says we're going to take a short break, but don't forget we're still running the After Earth competition, so stay glued onto your screens, guys, because the trailer's going to play, and then after the break, I'll give you more information on how to enter the competition, so stay tuned, Mindsetters. Welcome back, Mindsetters. I hope you're very excited about the movie, just as I am. Seeing Will Smith and his son doing their thing, you know, it's just too awesome. So to enter the competition, all you have to do is enter the keyword, grade 10s. Your keyword for today is law. Simple, L-A-W, law. All you have to do is go onto learnextra.co.za/After Earth, enter your keyword, and stand a chance to win yourself 2 tickets, a ticket for yourself and a friend to go watch After Earth. It does come out on the 7th of June, so do remember to enter, guys. Remember, competition does close tonight, 12 p.m. tonight it closes. So enter, go onto the website, you know, type in everything you need to do. Remember, grade 10s, your keyword, is law. I will post everything on Facebook, so go onto our Facebook page, facebook.com/learnextra to see all your information that you need for After Earth, guys. Enter this competition. It's very good for you to enter. You stand a chance to win yourself 2 tickets. And with all that said, Tracy, I think we should just, you know, start
Oh,
again.
yes. Who's going to say no to free movie tickets? Hello, I'm not. I'd enter, but I'm not allowed to.
We can be the friend, you know, because it's 2 tickets.
I don't have a problem
So
with that.
It's you and the friend, so we can
they
be
can
the
take
plus
me.
one.
Yeah, no, I can be a +1. I'm okay with that. I don't have. It's actually quite funny. I was talking to my learners today about this, and they laughed at me because they know it's the type of movies I like, and they just like shook their heads, and because we also were looking at some stuff, and they were like, "No, ma'am, seriously."
You just can't. You've passed the age limit where it's
Apparently, but you never get too old for sci-fi. I'm sorry. None of my friends my age want to go see it because they just don't do sci-fi. I'm like,
just
anyway.
for Will Smith. They can go watch it for Will Smith and his son.
Just Will Smith. No, his son's too young for me. Just saying, too young. Anyway, moving on. So, let's get back to the stuff that actually matters for now. Make sure you enter the competition, though. Now, in question, we're going to do a quick question. We have 3 resistors, 2 ohms, 3 ohms, 4 ohms, connected in 2 ways. We're going to calculate total resistance for both of these. So the first one says to us, calculate the total resistance when they are connected in series. So what that means is if we draw a quick diagram, I like to draw diagrams, it makes it easier. It means, so this is for part A. We have, there's my 2 ohm resistor, and there's my 3 ohm resistor, and there's my 4 ohm resistor. And they're connected in series. So remember I said to you before the break that if they're connected in series, it means that we just add them all together. So that's actually really nice. So we're going to go, my R total would be my 1 resistor plus my 2nd resistor plus my 3rd resistor. So it's just going to be 2 plus 3 plus 4, which then gives me 9 ohms. Okay? Grade 10s, sorry, I've been called everyone grade 9s today. Grade 10s, if you need to use your calculators, please don't be ashamed of that, okay? I know that for some of us, arithmetic isn't our strong suit. That's fine. It's why you're allowed to use a calculator. I also know that come exam time, you get quite pressured. And when you get pressured, you tend to make silly mistakes, and maybe this adds up to 10 or 6, or you multiply them together for some reason. Please just use your calculator, okay? Let's just make life easier. Part B says we take the same 3 resistors, but now we connect them in parallel, okay? So that means, and how they actually get put in, so whichever order you put your 3 in, it doesn't make a difference. So if you put the 2 at the top, the 3 at the top, whatever, doesn't make a difference because it all gives me the same answer in the long run. So that's what it looks like. Now we get to the fun part because we've got to look at our maths really, really carefully, okay? Now, this one gives me that funny, horrible equation, and I'm just going to do another color so we can see it, which says that 1 over R parallel, I'm using the parallel lines from maths, or you could say R total, because it's the only one there. We also use RP, so maybe let me do that to make it a bit easier for you guys. So 1 over R parallel, 1 over R1, 1 over R2, 1 over R3. Okay, fraction, so we go 1 over 2, 1 over 3, 1 over 4, and we go, oh, we don't like this. Hopefully you all know how to do fractions on your calculator. I'm very old school with this, so I go, well, I've got to find the lowest common denominator, which happens to be 12. Okay, so that means I would have to multiply the 2 by 12, so that's, by 6 to give me 12. The 3 gets multiplied by 4, 4 gets multiplied by 3, and we end up with, I just want to pull this down a little bit so I've got more space, 13, ooh, that's terrible, 13 over 12. But we're not done, okay? Because this is 1 over R parallel. Now, this is where you make your biggest mistake. We realize that it's 1 over R parallel, but we actually just want R parallel. So we go, okay. That means I've got to turn it upside down, and you guys do this. You go equal to 12 over 13, and then your teacher moans at you and doesn't give you any marks. Because mathematically, can I say that 13 over 12 equals 12 over 13? Of course not. Remember that this is 1 over R parallel, 13 over 12. So to get R parallel, I flip the whole thing over. So I've got to therefore, R parallel equals 12 over 13, which is actually 0.92. And it's tiny. How do I know that my calculation is correct? Because my total is smaller than 2 ohms. Hint, when you're calculating resistors in parallel, the total resistance in parallel will always, I'm sure you got that, always be smaller than the smallest resistance in the circuit, in the parallel section of the circuit, okay? Without exceptions. That's the thing about putting in resistors in series, in parallel, is that we can decrease the total resistance. So if I have a 1 ohm resistor and a 100 ohm resistor in parallel, the total between those two will be less than 1. You can even go do the math to double check me. Okay, so let's move on to Ohm's law. Now, Ohm's law is phenomenal, okay? I absolutely love Ohm's law. We're going to do another simulation, okay? Also with FET, we love it, and the link is actually on the notes. Ohm's law is now looking at the relationship between potential difference, voltage, and current over a resistor, okay? So what we're going to do is we're going to set up a circuit. I'm going to change the current in the circuit by changing the battery, keeping the resistor the same the whole way through, and then adding more cells and seeing what happens to the current and to the voltage over the resistor. Now, what I find so interesting about this is this was originally devised by a man called George Simon Ohm, who was a German physicist, actually, and he had a history in his father was a locksmith, I think it was, and so he learned how to manipulate metal and locks and all sorts of things growing up. And we consider simulation is even easier because it's all computerized, so I can do this in like 5 minutes flat, and we sorted. Even in your school labs, we can set up circuits with our fairly primitive circuit boards, and we can prove Ohm's law in about 10, 15 minutes, and off we go. We're happy because we have all the equipment. When George Simon Ohm did this experiment, and I really do think this is interesting, he couldn't just go to a hardware store and go, please can I have 3 meters of 0.1 millimeter diameter copper wire? And there he goes. Off. He couldn't do that. He physically had to make every single one of his wires because the diameter of the wire, the thickness of the wire affects resistance, so it would change some of his readings. So he physically had to make all of his wires. He physically had to make all his meters, okay, and work out how he was going to calculate potential difference in current. This took ages. It's not something you could do in a day. So he made his own equipment. He had to devise new ways of calculating things because it wasn't done at the time. So For us, it just seems like, so, oh, well, there we go, off we go. But it was a huge leap forward in our understanding of physics and electricity, and I think it's actually quite incredible what this man did with what was available. Okay, so what we're going to do is I need to put in an ammeter and voltmeter. There we go. So I have a voltmeter, which we'll use a little bit later on. And here's my cell. I'm going to drag a cell onto my circuit, so we have one. Okay, I'm going to have my little resistor over here. Let's put that resistor here. I'm going to keep the resistor constant. And I need an ammeter, which I'm going to turn sideways. No, actually, yeah, we're going to turn him sideways. We're going to put it here. You guys are going to be able to see it in a second. And I'm going to need a switch, because remember, I need to be able to switch on and off as I go along. So let's put my switch over here. And I can't really do anything with this because nothing is connected. Okay, and we know that for a circuit to work, we need everything connected. So what we're going to do is we're going to connect in our circuit. So I'm just dragging my wires. This is what I love about the circuit. And some of you go, why don't you just set up the circuit? I could, but this is just far more fun. And it'll actually go a lot quicker in a second once we get going. So what I'm doing is I'm making a circuit nice and simple, connecting in my wires. Let's just do that over here. We're going to put that one in over there. We're going to make sure our ammeter gets connected in. And there we go. And then we're going to connect in our last wire. And we have a circuit. Now, you're probably going, hang on, wait, Tracy, nothing's happening. Yes, nothing's happening because I haven't switched the switch on. Okay, remember, the switch has got to be switched on. It's got to complete the circuit. So what I'm going to do, though, is I'm going to put my voltmeter in place, connect it over my resistor. So there we go. It doesn't read anything because there's no current flowing. The ammeter doesn't read anything. No current is flowing. So now I'm going to switch it on. I switch it on. And very slowly, not very excitingly, we get some readings, and we go, okay, well, what we got there is, let's see, we have a current of 0.9 amps. Please just make a note of something here, though. All right, and I'm just going to quickly write it in. Over here, I just want you to note, oh, where did it go? Sure, it doesn't actually want me to write. No, it's not going to listen. Anyway, let's just close it. Okay. So just listen for me. Where it says amps, that's not an accepted abbreviation for amperes. It's got to be A. Please be careful. Now, for yourselves, we're going to make a quick note. We've done one reading, and we got 9 amperes, 9 volts. Okay, so let's go over here. We're going back to, I'm going back. Ooh, it's having a bit of a slow moment. Anyway. So here we go, and what we're going to do is we're just going to quickly set up a table. So, oh boy. Okay, the board is not liking me right now. So I think what we're going to have to do, grade 10s, is I need you to take some readings down as we go along, and then you're going to have to believe me, because otherwise we're going to be here till Christmas. What we're going to do now, okay, is if I need to right-click, I need to take this out. Okay, now what I'm going to do is I'm going to add another cell into my circuit. So here we go. Okay, by adding another cell, I can change the total current strength. I'm going to add in another wire. I'm going to switch it on. And last time, if I went voltage divided by current, I would have seen that I got 10. Okay, if I go 18 divided by 1,8, I get 10. Okay, it's a very specific reason why I'm doing this. What I'm going to do, let's add in, we're quickly going to add in another cell. Let's just switch this off. Okay, so I'm going to add in another cell, add in another set of wires. Let's switch it on. Come on, switch on. Now it's starting to go a little bit faster. It's a little bit more exciting. And what's happening here is we get 2,7 amperes and 26,99 volts. Okay, now if we go to our calculator and we go, no, I wanted the calculator. And we're going to go, because I'm going V divided by I, so I'm going to go 26.999 divided by 2.7. It gives me 9,996 we would need to round off to 2 decimal places, so this is 10. So this is okay, we're okay with that. So far we got 10. I can only give an answer to 2 decimal places because if I go back to my circuit, my most accurate reading is 2 decimal places from my voltmeter and my ammeter. I cannot give an answer to more than 2 decimal places because my meters don't go beyond 2 decimal places, okay? Now, what we're going to do over here is I'm going to change the voltage, and I'm doing it this way specifically because I want you to see something. So I'm just going to make it, I don't know, arbitrary value. Okay? Maybe a little bit less. It doesn't matter. Okay. Oh, it doesn't want to move. Let's make a... There we go. So now... No, that one works too well. Sorry, I'm trying to show you something particular. There we go. Sure, we're having a good day. There we go. That also works. Anyway, moving on. So, I've changed the voltage of that particular cell. Watch what happens. 4.27 amperes, 42.7. It's going to give me 10 again. Let's change. Let's look at that one. And let's change its voltage. And let's make it... there we go. So we've got 6.60 and 66.05. Now, if I go back to my calculator, because I actually do want to show you this. So let's put it over here, and we're going to go voltage, which is 66.05, divide by 6.6, gives me 10.007. If I was doing this for a practical investigation, and now I'm needing to record results, and I would be saying, find the value of V over I would need to record that V over I. Let's just switch that off. I would need to record that V over I as 10.01. Please don't record it as 10. You have to go to 2 decimal places. So you have to round off. Now I know that you're saying to me, but Tracy, I can see it's 10. I know you can. But this is what makes these simulations so absolutely fabulous. Because this is what you would get in a real-life situation, okay? You won't get exactly the same answer every single time. Because, number one, this is only true, this resistance being constant is only true if temperature doesn't change. Now, we're all human. So sometimes, like I've actually left, if I had left this, if this was a proper circuit and I'd left that circuit on, this resistor would be getting hot. With the resistor getting hot, resistance changes. So that would vary my results, okay? Number two, you know what? We're lucky. We have digital ammeters and digital voltmeters in here. Sometimes we don't. And without having digital ones, it becomes more and more difficult to read what we have. The more difficult it is to read, the less accurate it becomes, okay? And we've got to stick within the accuracy of our meters, okay? Now, we could do this forever. I could set up hundreds of results using the simulation, which is what I love about it, okay? And we could do this for a very, very long time. And we will all get the same sort of thing. Now, we realize that we're getting round about 10. I want to show you something. This resistor, let me do it, I need right click, sorry. This resistor already has a resistance of 10. So they decided on the circuit, whenever you put a resistor in, it starts off as 10 ohms. If you go and look at all those different values we just did, you realize that you got 10. V divided by R by I gave us approximately 10, very close to 10 within 100th. That is amazing. It gave me a constant. So what V divided by I was actually giving me was resistance. Okay? So that actually gets us to state Ohm's law, which says, so we're going to move on. Ohm's law says to us that, before we get there, sorry, I'm having a good day. If we have to graph potential difference versus current, potential difference versus current, we get, and I'm not sure you can actually see it, so I'm just going to help it along, we get a straight line, okay? And that straight line must go through 0, must go through the origin when you draw it, because if there's no voltage, there's no energy, there's no current, no resistance. Can't be resistance if nothing's moving. When you draw this, so if you get a set of results and you go and do this and you draw the diagram, the graph, line of best fit. You plot all your points, okay? And in fact, I did this with a group of my learners today, and I used exactly the same simulation, which was really nice. But what we found, which I found very interesting, is they got their points, they plotted their points, and then for some reason, there was one, that went over here. Okay. Wow. That just arbitrarily, sorry, I've got some extra points because me and the board aren't talking right now, but there was a point that just went off to one side. That's fine, you don't include it, you don't draw it, line of best fit, okay? This line, this gradient is R, because R equals V over I. Okay? So I think what we're going to do, Looney,
Yes.
is I'm going to let them digest
Okay.
what we've just done, and we'll finish it off in the next section.
Okay. Mindsetters, don't forget to enter the After Earth competition. I did post the code word onto our Facebook page. It is law for you grade 10s, so make sure you enter and stand a chance to win those 2 tickets. We are going to take a very short break, so stay tuned and we'll be back right after this. Welcome back, Mindsetters. If you've just tuned in, we are going through electric circuits with Tracy. Remember that you can go onto koreandaba.co.za to register yourself and your friends. If you're confused, guys, you don't know if you want to be a doctor, a lawyer, an artist, if you're just confused about your career path, grade 10 to 12, you can register yourself on Korea and Daba. I did post all the information on our Facebook page, so just hop on over to the website and register yourself. Remember, Mindset will have a table there, so we will be there. You'll see me and all the other presenters, and we'll just chat, and just ask us anything you want to ask. But right now, though, we will hand over back to Tracy. And Tracy, we do have a question from Errol. He's asking, can you please explain why a battery in a circuit goes flat eventually?
It's a great question, Errol. It's a little beyond what you're going to do this year, but essentially what happens inside a battery, remember, a battery is a chemical reaction, and let's ignore the rechargeable ones, and it's a one-way reaction, okay? And what's actually happening is there's a transfer of electrons and ions from one side to another, and in fact, what actually happens when a battery goes flat is not that the reaction has stopped, but it's reached a point of what we call equilibrium, and it's reached a point where there's no longer a difference in energy between the reactants and the products eventually. So because there's no difference in energy, the electrons aren't forced through the circuit anymore. With a rechargeable battery, we can put it into a socket, and it actually forces it to go back the other way and then gives it more energy. But even that's got a lifespan. So you can only recharge a rechargeable battery so many times, and most packets tell you how many times. I mean, you guys all know. You know when your cell phone, when it comes down time to upgrade, and like you have to charge your phone every 10 minutes because all you did was go on those social media network things. Or
Can I just very quickly?
Let's do.
Emmanuel is asking us to send a shout out to him because he says that his parents think he's playing with his phone when he's looking at the links. So Emmanuel, to prove to your parents that you're not playing with your phone, hi, thanks for watching.
Oh, excellent, Emmanuel. Well done. Parents, he's doing a good thing. He's learning. Okay, so let's quickly do this, okay? So before the break, we said R equals V over I. All right, it's a straight line for the graph that we got, which is a brilliant thing for us because the straight line means that we have a direct proportion. If I double voltage, I double current. Has to be. And that actually brings us to the statement of Ohm's law, which is here. And it's one of those that you have to learn. The potential difference across the resistor is directly proportional to the current through the resistor, provided the temperature remains constant. Please, 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 this part that I would put in brackets if I didn't have the eraser on, that I've now put in brackets, guys, that's a non-negotiable in the statement. And that breaks my heart because we ask the same in a matric exam and then we go and mark it and then we have to give you naught. Because the statement isn't just that potential difference and current are directly proportional to each other. Temperature plays a big role. You've learned that. Okay, you've done this before, that when we increase the temperature of a resistor, we increase the resistance. So temperature is a very important factor. As an equation, we can say that R equals V over I. Okay? It's actually straight from the graph because R was the gradient of my graph. This is wonderful. Now, what does this mean? Well, R is resistance measured in ohms. B is potential difference measured in volts, and I is current measured in amps, okay, or amperes, not amps, amperes. Please never ever call it amps. Naught, it's not accepted units. It's an English colloquial, okay? I'm not sure where we get it from, but it's an English, it's the way we speak in English, and we shorten it, abbreviate, that's what I'm looking for, abbreviated to amps in English, but it's not amps, it's amperes. That actually brings us to what we really need to get down to, and that's calculations. So we starting with, like, let's do really simple ones. These are the ones that we hopefully don't struggle with, but you know what, guys? Take it slowly, let's work through them, follow my method, and you'll be fine. This question says to us, calculate the resistance. So they're saying what is R, so that's my unknown, if the potential difference, so that would be V across the resistor, is 9 volts, and the current through the resistor is 3 amps. Guys, please write a data list. Write it to the side, write what you're given. It's going to make your life a lot easier along the way. So this means that R equals V over I. Substituting what we know. So that gives me 9 divided by 3. And hopefully we can do this in our heads, but if not, we take out our calculators. 9 divided by 3, that gives me 3 ohms. Okay, looks like a little Mexican hat. Not as nice as when it's typed, but hey, it's still the right thing. We know what you're talking about. Nice and simple. So remember, you need to put your equation, you need to put your substitution, you need to put your answer with the units. Don't forget the units. Nothing difficult about what we've done. Let's do another one. Next question says to us, so, if the current, okay, so the current through a resistor is 1.5 amps, so they're saying to me I is 1.5, and grade 10s, as you watch me do this and the things I write, I'm actually talking through the thought process that goes on in my head. So the things I'm saying to you, I'm not just saying to you because I'm trying to teach you something, which I am, but that's literally when I do a question like this and I'm doing a memo to an exam or I say a question for the first time, this is exactly what I do. I underline things, I ring things, I talk it through in my head. So must you, okay? So we've got a current through is 1.5 amps, has a resistance, so that's R of 4 ohms. What is the potential difference? So V is my unknown. At this point, there is nothing wrong, grade 10s, with you taking R equals V over I, swapping it around so you've got V equals I times R if you're comfortable with the maths. And you know, you can get it right. I worry, however, and I see this all the time, you're in a bit of a rush, you get confused, and next thing I have an equation that says to me V equals I divided by R, or V equals R divided by I. I see it all the time. You then get naught, nothing, no matter what you do after that, because your equation is incorrect. And remember, on your information sheet, you get given Ohm's law as R equals V over I. Please use it like that, grade 10s. I'm begging you. Also, next step, put in what you were given. So I know is 4, V is what I'm looking for, and I is 1.5. If from this step, you can do the maths and you know to multiply, you don't need to show me, off you go, on your calculator, we're sorted. However, if you need to, and you know what, grade 10s, do it. Please don't be ashamed of it. If you need to do the extra steps, in other words, if you need to go, v must then be equal, so I'm going to have to multiply by 1.5 on both sides. Please do that. Okay? Why lose marks because you don't want to look silly? You look silly when you lose marks. Don't. Okay? I would rather you did that. And then if we go 4 times 1.5, and I just want to show you. Okay, so we go 4 times 1.5, and it's 6. Nice and easy. So that gives me 6 volts. Okay, 6V. That wasn't so bad. Nice and simple. But now we're going to be careful here, because I worry that you're looking at these numbers and going, oh, they're nice, they're easy, they're small, they're not a problem. Yeah, but think about when we calculated the resistance, and the total resistance in parallel was 0.92. There is absolutely no guarantee anymore that you're going to get nice numbers. So you're not necessarily going to get 1.5, 1.25, 2.75 like we used to. Okay? In fact, we're trying to make your science more realistic, so you are going to get funny numbers. Think about what we saw in the simulation with the voltage. I mean, it was 27, something 2. Or I did with my learners today, and we got readings of 26.99. That is not nice to work with, but that's the way it is, okay? So, what do we have here? A resistor. Resistor has a resistance of 15 ohms. So R equals 15 ohms. Calculate the current. So that's I, that's my unknown, through the resistor when the potential difference across the resistor is 20. So V equals 20 volts. Okay, so we go fine. Let's see. R equals V over I. We start with the equation. Okay, so we get 15. And we're going to have 20 divided by I. Okay, now we're going to, this one's slightly different than the voltage, okay, because now we want to, the 15 and the 20 are going to swap places because of the, because I is at the bottom of a fraction. So I is 20 divided by 15, and this is actually a very typical type of answer, actually. 20 divided by 15. Now, on your calculators, if you look at the screen, what is the calculator giving me as an answer? 4 over 3. Grade 10s, that is not your answer. Please be careful. In maths, depending on the question, that is an acceptable answer. You can leave it as 4 over 10. 4 over 3, sorry. Not in science. Never, ever, ever do you leave an answer as a fraction. Because all that fraction is a simplification of your substitution. It's not what I want. We have to have it. And look at that. Didn't even do what I wanted there. Oh, you kidding. Okay. So, now we get another, and I'm actually had this happen. Now we go, hang on, wait. It gives me 1 1/3. We don't write it like that either. So what I'm going to do is I'm going to change the mode. Okay, so we're going to go to, on your calculator, for science, you really need to have it in linear mode. Okay, because now watch what happens. If I go 20 divided by 15, it gives me 1.33. That's my answer. So what I need you to do, grade 10s, take your calculators off maths display. Put it into linear mode. Then you will not be tempted to leave an answer as a fraction, because it will not leave an answer as a fraction. Okay, this is so important, grade 10s, because it's going to bite you in the bum later on, all right? So this is 1.33 amperes. I don't put the dot on the top to indicate that it's recurring, even though the 3 is recurring. If this had worked out to, say, 1.666666 recurring, I would round it off to 1.67. Please round it off 2 decimal places. And if this was one that I would say now need to use in a further calculation, which I'm going to show you next week, I would use the rounded off value. Okay, don't store the value into your calculators. I argue with people all the time over this. We have lots of fights in my classroom, especially with the people who are like pure maths, and they go, no, I want to keep the decimals. I know you do, but don't. 2 decimal places, use the rounded off numbers. Okay, now, Looney, do you have any questions, or can I do a quick summary, do you think?
You can do
because we don't have a lot of time.
We don't have any questions. You can do a quick summary.
Oh, I'm going to have to do a quick summary. Apparently, I don't think I'm brilliant. So, remember what I said today. Resistance is R. Resistors can be measured can be connected in series or parallel. We connect them in series in order to increase the total resistance, which decreases the total current. We'll connect them in parallel to decrease the total resistance, increase the current. Then we looked at Ohm's law, which says to us that the potential difference across a resistor is directly proportional to the current through the resistor, provided the temperature remains constant. And the equation for that was R equals V over I. Okay, remember, for the total resistance of resistors in series, we just simply add them all together. When they're in parallel, we go 1 over parallel, 1 over R plus 1 over R plus 1 over R. We calculated, and then we flip them all over at the end, okay? Now, all of that is foundation, because next week we're going to tackle the fun part. I want to encourage you to have some colored pens with you. I'm going to have fun with the highlighters on the board. It's going to be lots of fun. We're going to do circuits, and we're going to hopefully get it done. And that's me.
All right. Mindset says, I'd just like to congratulate Priyashka Inderjit. I hope I'm pronouncing your name right. You have won yourself 2 tickets to go see After Earth. I did post it on Facebook, so congratulations to you. Guys, great hands, I'm so glad to be on this show. I hope you guys enjoyed it just as much as I did. Make sure you do tune in next week for more Learn Extra. See you then.
To flow. They can move from one side to another as long as we've given them energy, okay? How well or how badly they move depends on resistance. It depends on the structure of the metal inside. Now, remember, last week we defined electric current as the flow of charge, which can be either negative or positive, but specifically in a conductor, it's the flow of electrons. So with electricity, we are concerned with the flow of electrons because it's the valence electrons that move from one side to another. A good conductor, which is what we want in circuits most of the time, has very little resistance. It allows current to flow really easily. However, we get bad conductors. Bad conductors are actually good. That sounds a little bit of a contradiction, but they are. Because we can make use of the fact that they're bad conductors because they offer resistance, and we can make use of that in our circuits to perform different functions. So in a traditional light bulb, for example, we use the fact that tungsten, the filament, gets very, very hot because it has a very high resistance. But it gets so hot it burns white. It has that white, bright light that we can use. That's a good thing, okay? Now, wrong way. Let's go forward, shall we? Because we've done that. Now, what is a resistor? Well, first of all, we're going to define a resistor. It is a component in a circuit which does exactly what its name says. It resists the flow of charge. We spoke about current, and now we need to talk about a thing called resistance. But before we get there, let's just talk about what we are going to do today. We are going to discuss resistance in an electric circuit, what it is, all of that sort of stuff. We're then going to look at resistors in series and in parallel, because that's really important how they're connected. We're then going to define and discuss Ohm's law, very, very important law, and we're going to do a couple of calculations using Ohm's law. Okay? So we're still keeping it fairly simple. Next week, so make sure you don't go anywhere, next week we're going to do the more complicated circuits with circuit diagrams and that sort of thing, okay? But first of all, let's just talk about the whole concept of resistance. Now, we know that in an electric circuit, we put metal conductors in because they conduct electricity really well. Now, what is actually happening is the electrons are moving from one part to the other, but how is that possible? If we look at the metallic bond inside a metal, remember that inside this bond, we're going to have our positive cause, this part here, okay, and I don't think you can actually see that. Let me do it in another color, say, put it in white. So we have our positive cores, which are stationary, okay, to a certain extent. So they are the nucleus with the inner electrons of each of the metals, and then around them, we have our delocalized electrons. Remember, those are the electrons that would sit in the valence shell of a metal. Those delocalized electrons can be given, when given enough energy, will move through the conductor. So it makes it difficult for the electrons to move through it. It is generally a bad conductor. It should be a bad conductor, but it's still going to be metallic, okay? So we're not going to go and put in an insulator. So please understand the difference. I'm not going to put plastic into a circuit because it's a bad conductor, because it doesn't conduct at all, and in fact will just melt and burn, and it's just silly. So when we talk about resistors, they're still going to be metallic, okay, or semiconductors, so metalloids, but they still going to be able to conduct a little bit. They're just not very good at it. So they're not as good as, for example, copper. Copper is a great conductor, so it's not good for a resistor. It's said to have a resistance, and its symbol is R. So whenever we put resistance or a resistor into a circuit, or we put it into an equation, we use R, okay? Now, what happens with the resistor? Well, electrical energy is converted into other types through the resistor. So, and most of the time it's heat, but we can get light, maybe we get sound, maybe we get kinetic energy, all sorts of things can happen here, okay? And resistors can be connected in series or parallel. Now I want to show you a quick simulation. Remember, we use FET all the time. I absolutely love that website, phet.colorado. It is absolutely amazing. Get so much really cool stuff in there. Now, what I've got over here is a simulation where it's a simulation, okay? So it's exaggerated, but we can deal with it. We have a battery in the middle, and
Welcome to all you grade 10 mindsetters. It is a Tuesday. That means we're doing physical sciences. I am Looney, and joining me in studio today is Tracy. Tracy, how are you doing?
fine, and you?
I'm good, thank you.
It's nice to meet you.
I know, hey? Thanks
Yeah.
for having me on a
Oh,
Tuesday,
it's okay.
finally.
Anytime.
So what are we doing on today's show?
Well, today we're going to do circuits. We started that a little bit last week, a little bit of introduction. So today we're going to do resistance, we're going to do Ohm's law, and we're going to do a couple of calculations. We're going to really cool, fun simulation to play with. So I think it's going to be a good one.
Mindsetters, you heard it. Electric circuits. Science, guys. It's all that stuff. I did it at school, but then it wasn't my favorite subject. But anyway, guys, to keep in touch with us on Facebook, make sure you go onto facebook.com/LearnExtra. Our handle on Twitter is @LearnExtra to download all your show notes, the videos, the schedules, past exam papers to get you prepared for the coming exams. You can go to learnextra.co.za/live. Guys, we also have Korea and Durban coming up. It's from the 20th to the 22nd of June. So make sure you go register yourself. It's for free, and Mindset will be there. You can meet me and all the other presenters. You can go into koreaanddurban.co.za. So all that said, I think, Tracy, we can start the lesson.
Thank you, Lini. Okay. Well, guys, we're going to go straight into it. Like I said, it's the second part of electric circuits. Last week we spoke about potential difference. Over here, the little, I'll stand this side because there's actually more of the stuff on that side. We have an ammeter which is connected to a windmill. Basically what's happening is when I play this, I just want you to see, don't worry about everything else that's happening. The windmill turns because it's like water falling on it, okay? And what we're going to do is I'm going to just make the resistance a little bit more. So I'm increasing the resistance to make the voltage a little bit less. Let's make it to or thereabouts. So I've changed the resistance, I've changed the voltage, and I want you to see something. First of all, on the hot-cold meter, if you watched, it actually is got cold. I'll speak English for you too. The current is quite low, but this also has a fairly low resistance, which is fine. But if you watch carefully, as the little blue electrons are going through, you can see, and they're a browny grey color, inside my resistor, which is the big box. Okay, let me just, so the resistor, so now we've got a shot of it, is this part here. Okay, that's what when I'm talking about the resistor, it's over there. Now, what I've written will disappear, so just watch carefully. The electrons are my little blue things that are going around, and these funny funny grey circly things that are bouncing up and down. Those are the cores. So that's referring to the inside, the metal cores that don't move, they can't go anywhere, they can't move backwards and forwards, okay? And over here, let me just take that away.